Welcome everyone. Today we will do today in the 8th tutorial of your introduction to classical mechanics course, we will do some more problems on moment of inertia and rigid body. Okay, so in the last class I have calculated the moment of inertia of various types of object like a triangular lamina here, also a rectangular lamina, a circular lamina. Then I calculated the moment of inertia corresponding to a cylinder, and also I solved the example with the with the varying density, that is where the density was not a constant. So this type of problems I have solved in the last day. Now today we will continue to do some more problems of this moment of inertia, related to this moment of inertia. So at first we will calculate the moment of inertia of a spherical cell and a solid sphere, and then we will do an application of this moment of inertia of the solid body, spherical solid body. Okay, now let us start. So at first I will do for spherical cell plus solid sphere. Okay, so for a spherical coordinate, so you know that x, y, z, if we transfer it from r, theta and phi, so this is a position, so this will be your phi, this will be your theta, and the distance will be r. So if we go from x, y, z to r, theta, phi, then this figure I have not maybe it is that I have not done it accurately. I have not given much attention to x, y, z and r, theta, phi. So as you all know that x is actually written by r sin theta cos phi. So just a second. Spherical coordinate. Yeah. So if you take a proper spherical coordinate, then you can write x equals to r sin theta cos phi, y equals to r sin theta sin phi, and z equals to r cos theta. So I think I have taken it in a correct way. So you can check z r cos theta is right, x equals to r sin theta cos phi. I have taken it in a correct way. So this is your x, y and z, and your volume element will be r square sin theta dr d theta d phi. So these four things you should always remember, then you will get benefit while you are doing a calculation. Now for a spherical cell, suppose it is a spherical shell, so the thickness of the cell is dr, let us say it is dr, and the radius is r. So the all the inside part is actually hollow, so it is a hollow spherical cell. Okay, now if we calculate the moment of inertia Izz, so as you know I am not writing the full equation because you have already, I think you are already familiar to this part. So it will be x square plus y square rho 0 dV. So the rho 0 dV is actually the mass, dm, elemental mass. Okay, now if you substitute your x and y in terms of theta and phi, then you will get, it will be r to the power 4, just put this r sin theta cos phi and r sin theta sin phi. So r to the power 4 dr sin cube theta d theta d phi. So just check it. I think you will get this, and there will be a rho 0. So what I have done, I have substitute x and y in terms of theta phi, and as well as the dv volume element, I have written it in terms of this r square sin theta dr d theta d phi. Okay. Now for a spherical cell, we don't have to do the integration over r, because the width is only dr, and below dr, I mean the inner part of the dr is exactly hollow. So we can take out our r dependency from the integration, and the integration will be sin cube theta d phi rho 0. So it is for a spherical cell. Now the same integration we have to do for the solid body, but in that case, so for the solid body the difference will come in the first term. So for a solid body there is no hollow space inside the I mean inside the width of the perimeter, I mean dr. So for the solid case, it is solid from center to the outer radius. That's why we have to do the integration sin cube theta d phi. So in the sphere case, in the solid sphere case, we cannot take out our r4 r to the power 4 dr out of the integration. It is the main difference between the two. So if you continue to do it, so for spherical cell your result will be rho 0 r to the power 4 dr 4/3 times 2 pi. It will come from this integration. So and also for a shell, the volume is actually 4 pi r square dr, where dr is the width, times the rho 0. If I multiply the volume with the rho 0, that will give you the mass. So it is the mass of the cell. Okay, let us call it as m. So if we substitute this m in the equation, so if we substitute this in terms of m, then we will get the result as 2/3 m r square. Okay, so where m is actually 4 pi r square dr rho 0. So this 4 pi r square, you will take r square from here with dr, so that you will be left with one more r square. So that r square is here, and the numerical factor you can check it. It will come as 2/3 m r square for the spherical cell. Now what will happen for the I mean solid body? So for solid body, the volume will be 4/3 pi r cube, okay, and multiplied with the density. So it is the mass of the solid body. Okay, so here if you do the integration, you will get, I mean okay, yes. So here one thing, here you can consider that you are doing the r integration from 0 to capital R. Okay, so this integration will be done from 0 to capital R, where capital R is the radius of the sphere. So it will be actually capital R cube. So it doesn't matter if you write it smaller, but to differentiate I am writing it as capital R, and this result you will get. So r to the power 5/5, this factor will come extra, where in the previous case it was not there, and the other the integration you can do it. So by doing this, I am not doing okay, so I can do it rho 0 r to the power, it will give you I think 4/3 times 2 pi. Okay, and rho 0 is there, so I forgot the rho 0 here. Now if you write 4/3 pi r cube rho 0, 4/3 pi take r cube from here and rho 0, then that will be your mass, and you will be left with this 2 and this 5 factor. So 2 5 m r, and 1 r and r square factor will be there, because you have taken the r cube. So this is the moment of inertia of a solid sphere, that 2/5 m r square, and this is for the cell, that is 2/3 m r square. So all these are important, and if you can remember these values, these are very simple to remember, then you can do many problems. Now one problem I will do. Okay, so just remember this 2 point. For cell it is 2/3 m r square, where m is the mass of the cell, and for solid body means solid sphere, it is 25 m/r square. Okay. Okay, now we will do an interesting problem, a sphere with spherical cavity, just an application of this thing. Okay, but before doing that, I need to tell you about a theorem. In the previous day I also told it, but today I will do it in a more broad way. Parallel axis theorem, it is very important. So I will not do the detailed calculation, I will try to give you the idea. So suppose it is our coordinate system x, y, z, and this is the body. Okay, so this coordinate, this dashed coordinate, is actually in the body. You can call it as a body system, and the center of the body system is taken at the center of mass of the body, that is g. Okay, now if this, and then the center of the xyz is this o. Okay, where o is at a distance from the g, I mean the body coordinate and the lab coordinate, you can say xyz lab coordinate are different. Now if the body, suppose the body is rotating, and you are, suppose the body is rotating and you are watching that body from a distance. I mean the observer is sitting at O and it is watching the body which is rotating. So in this case, you can write your moment of inertia with respect to your axis. So suppose we are writing Ixx. Okay, so Ixx is actually measured by the observer sitting at O. Okay, and Ig is the moment of inertia measured at body frame, I mean with respect to that capital G. So if this is the case, then you can relate the Ixx and Ig, that means the moment of inertia measured by the observer with the moment of inertia with respect to the body frame. So in that case, your Ixx will be Ig plus m a square. So what is m? M is actually the total mass of the body. M is mass, and a is actually the distance between A is the distance between the center of mass g from the OX axis. So why OX axis? Because we are calculating Ixx. Similarly, if you calculate Iyy, then your distance A will be distance of g from the OY axis. Okay, so if I am doing it Ixx, then the distance will be this, which can be written as also plus m x square plus not x square plus m y square plus z square, if the coordinate of this particular g is so say g is xyz, the coordinate of g is xyz, let us say bar to differentiate from this axis. So it will be y bar square plus z bar square. Okay, so similarly if you calculate Iyy, it will be g and then m. Now the distance will be the distance of g from the OY axis instead of the OX axis. So that will be O x square x bar square plus z bar square. Okay, so this is an important thing. Now again, so okay, so this is called the perpendicular axis theorem. So more simple way we can say that, now suppose this is a rotating body, small rotating body, which is rotating with respect to its center of mass. Okay, so and we are measuring from this particular point. So it is rotating at point O, rotating around the point, around the axis which is passing through O, and we want to measure the moment of inertia at A. Okay, now you can see, so let us say is the z axis. This is z axis. Now just now I have calculated one sphere which is rotating around z axis is izz is for sphere, let us go to the sphere 25 mr square. Okay, so for a sphere izz is 2 by 5 mr square when it is rotating around z axis, which is the body axis. Okay, so this particular ball like system, it has a moment of inertia 25 mr square with respect to oz axis. Okay, and let us say that this distance is a. Now if you want to calculate your moment of inertia from a, just do the ig plus mass of the body is, I have taken small m, a square. So ig, your ig is already calculated. Okay, so you can see this is your moment of inertia of the body with respect to a point a. I mean you can think of as a axis, so capital X, let us say call it as capital X. So the moment of inertia of the spherical body with respect to capital ax axis is just the sum of the moment of inertia along oz axis plus the distance of O from the A point A. And in our previous assignment I found a problem which is like this, and there are two systems, two ball like system which is rotating and that is connected by a rod L, so 2L. So as so you can say that if it is connected by 2L, so L is in the left half and L is in the right half. So our A is actually L in that problem, and in that case you can calculate your the moment of inertia of the system as actually it is a sum of two balls, two different balls. So if it is 25 mr square plus ms square for one ball, in that particular case when there are two balls, it will be nothing but 25 mr square plus ms square. So a instead of a I am writing as ml square. Okay, so it was in your option, you can also check that your moment of inertia will be this one. And one thing to mention that this ia is actually ia, I mean izz at the position of a. You can think it as like this. Okay, so similarly you can calculate ixx in with respect to position a. So all that you can do. If you do that, I think okay, yes, oh sorry, there is izz is actually, it is along the x axis. Okay, let us say it is along the x axis, so it is yeah, I think I have done it in a correct way. Yes, izz, because ixx will be 0 for this case. Okay, so you can check that also, because for ixx your I mean if you write your moment of inertia tensor, you can find that that is 0. Okay. Yes, so let's go ahead. Now so now we will do a problem, as I told you, a sphere with spherical cavity. This is the same type of application. So suppose we have a sphere like this which have a body axis like this, and we have another small cut, I mean this is the cut in the sphere. Okay, so this part is actually hollow. Okay, and this particular, so let us say it O, this is y, this is x. Okay, and the distance of this hollow cut from this y axis is x. Okay, and say the small, I mean the radius of this hollow part is r, whereas the radius of the full sphere is capital R. Now we will see the application of this perpendicular axis theorem in this problem. So okay, now the first thing is that our and we will calculate the IYY component. Okay, now our IYY component for the total sphere, which I am writing as IYY and with a notation S, that is actually IYY SC and IYYC. So I will tell what is it. This is the total moment of inertia of the sphere when there is no cut. Okay, now this is the total moment of inertia when there is cut. So total mi when the cut is present, and it is the moment of inertia of that cut part, I mean that hollow part. Okay, so moment of, I mean that hollow part, if you cut a sphere like this, then the hollow part you can take it as a I mean solid body. So that is a moment of inertia of that cut part. Okay, so okay, now if we consider this hollow part when it was already in the sphere, at that time it was a solid body. So before cut, I mean after cutting it has become hollow. Before that it was the full sphere was a solid body. Now this ICYY, which is the moment of inertia of cut part with respect to this OY axis. Okay, now this axis OY axis is actually 25 m r square, where small m is the mass of the cut part plus m x square. Okay, as I told you that this this is exactly the parallel axis theorem. Okay, so your body is rotating from at a distance from the center of your coordinate system, then it will be a sum of the distance between the center of system and the center of mass of that body plus the moment of inertia with respect to that body axis. Okay, so this is the moment of inertia of the cut part. Now the total moment of inertia when there was no cut part, only the and only the solid volume was existing, solid sphere was existing. So in this case the solid was 25 m r square, because it was rotating as a solid body and there was no cut part. So capital M is the mass of the solid body, and it was like this. So here capital M is actually 4/3 pi r cube rho 0, and small m, which is the mass of the cut part, that is pi r cube rho 0. So this is the difference between capital M and small m. Now just you can substitute your ISYY and ISC. Sorry, I should have no, yeah, ISYY. Now if you substitute your ISYY, ICYY in this particular equation, you can find your ISCYY, which is actually the moment of inertia of the body with the hollow cut. Okay, that is ISYY minus ICYY. So this will be 25 m r square minus 25 small m r square plus m x square. So this is the moment of inertia of the body with the cut. So this is the moment of inertia of the full body when there was no cut. This is the moment of inertia of the cutted part only, and this is the moment of inertia of the body with the hollow cavity. So not cut, but I should say is as a hollow cavity. Cut is not good. Okay, so this is just an application of this perpendicular axis theorem, which where in this part we have used that perpendicular axis theorem to calculate the moment of inertia of the hollow cavity. Okay, so any problem till now? Squares are not good enough. Yeah. Okay, so this is a problem, interesting problem. Now what is the time? Just a second. Okay, now we will calculate, we will do a problem. I mean, it is a fundamental problem of classical mechanics, and I like to do this type of problems. Okay, okay, so suppose this is a just a second. This is a plane. I mean, this is a plane which is making an angle of theta with respect to the horizontal direction. Let us say ABC. Now a cylinder is rolling down from the A point towards the C point. Okay, and here we will not consider it as a point mass particle. It is a solid 3D cylinder. Okay, now we will calculate how much distance it will travel in a time t along that AC path. Okay, so let us start, and we will use our concept from this chapter also. So as I showed you in the previous day, sorry, yeah, you can see this was calculated. Yeah, this was calculated. I mean, I have calculated the moment of inertia for a cylinder. So for a cylinder, the IZZ, that is the rotation around the axis, around its own axis. So it is the OZ. So it is the OZ axis, and IZZ means the rotation around this OZ axis, that is the axis of the cylinder. So that is that comes out as half m r square, where m is the mass of the cylinder. So we will use this fact in this problem. Okay, so and as it is rolling from A to C, it is rotating around its own axis. Okay, so I cannot I mean draw the cylinder in the 2D plane, so you can understand so why it is looking like a sphere. It is actually not a sphere, it is a cylinder, and only this part we are seeing from this direction. So that's why it is looking like a sphere. So the I is actually half m r square, where r is the radius of the sphere and m is the mass of the sphere. Okay, now we will consider this level as v equals to 0. I mean 0 potential level. We can do that in our problem, because always in problem of classical mechanics the potential difference matters, not the exact value of the potential. Okay, now we will do the conservation of mechanical energy at point A, and suppose after time t it has reached a point E. Okay, so let us call it a small h, and it is capital H, and this distance call as S, from A to E, sorry. Okay, so at A the total energy will be mg cap h, that is the potential energy, h is the height, plus it was rest at A. I mean we have put the cylinder at A and then it starts rolling, so the other energies are 0. Okay, and at point E, so there is rotational energy plus kinetic energy, I mean kinetic energy plus the potential energy, and plus energy due to the rotation. Okay, so 3 parts are there. One is mg, and potential energy is h minus capital H minus h, because this is the capital H minus h part, which is the potential energy of that E, plus half mv square, where v is the velocity, and plus half I omega square. Okay, so where I is the moment of inertia and I omega square is the rotational energy of the system. Yeah, kinetic energy due to rotation, and half mv square is kinetic energy due to the translation. V is the translation velocity. So according to the conservation energy, these two must be same, and as we have not considered any friction, okay, so there is no friction and there is no dissipative force, all the forces are conservative. Okay, so it the conservation law will give you this. Okay, now yes, now And as we have not considered the friction, as well as we will not consider the slipping. I mean, the body is rotating, but during the rotation it is not slipping. Okay, only the pure rotation is there. So if you consider that, so for pure rotation you can write your v, which is the velocity of the translation velocity of the cylinder, as omega r. Okay, where omega is the angular velocity and r is the radius of the distance, radius of the cylinder. So v can be written as omega r. Now if you write it like this, so your mgh and mg capital H and mg capital H will be cancelled out from the both side, and small mg small h will we can take it as we can take it on the left hand side. Then it will be half m v square plus half I omega square. Omega we will substitute as v square by r square. Okay, and also that I we can write I as half mr square also. Okay, so we will do it in a more generic way, so that you can apply it for other bodies also. So we will write as, let us say, I is equals to mk square, where k is the radius of gyration. We know that I is half mr square, but instead of writing half mr square, sorry, let us call mass of the cylinder is small m. Okay, so instead of writing half mr square, I am writing half mk square. So if you compare this with this, you can write your k square is equals to half r square, nothing different. Okay, so if we write it like this way, so why I am writing it in terms of k, because suppose you are considering a sphere. So for the sphere it will not be half mr square, right? For the sphere it will be 25 mr square. So for that case your k square will be 25 r square instead of half r square for our case. So you can put your k square accordingly for your different system. That's why we have written it in terms of k, so that you can substitute your k with the system and you can get the result. Okay, so half this will be mk square v square by r square. Now this will give you 1 plus k square by r square. Okay, so your v square is 2gh by 1 plus k square by r square. So you can see why we have written k square in, I mean, not writing the proper form. So if it is your cylinder, then your k square by r square is half actually. For a sphere, your k square by r square equals to 2 by 5. So if you just substitute the value according to your body, and you can get the result of your velocity, which will be the velocity at point E after time t. Okay, so this is the this is v. Now yes, now okay, now if you write as we are considering the cylinder also, let us consider the k square by r square equals to half. So 1 plus half, it will be 3 by 2, that means it will be 4 by 3 gh. Okay, small h. And according to the figure, this small h, which is this one, this to this distance, so this small h you can write it as s sin theta, right? This is h, this is s, that means h by s equals to sin theta. So h is equals to s sin theta. So this is 4/3 g s sin theta. Okay, so this is now your equation, and so it is like a differential equation, g s sin theta. Your theta is constant, and if you, I mean, write v as d s dt, that is 4 by 3 g sin theta, and by integrating both sides you can get the result. I mean, what will be the distance s after time t, right? So yes, I have. So if you write as k a0 is to the power half, where you have defined your a0 as 4 by 3 g sin theta, that you can do. Okay, then ds by a0 s to the power half is equals to dt. Just do the integration from 0 to 2 and 0 to s, then you will get your result. So you will get that, just do the integration at time t, the distance s, which is I have written as s in the bracket t, it will come out as 1/3 g sin theta times t square. Okay, so this is the distance which the body has covered in a time t along that slanting plane, which is the AC plane. So what I mean, in which section our concept of rotational energy and moment of inertia comes, that is the main important section is this one. So you have to you need to know the rotational energy. So for rotational energy I, this I is actually coming from the concept which we have learnt in this section, that is half mr square, or for a sphere it is 25 mr square, and from using all those knowledge you can calculate the distance from the conservation of energy of this particular system. Okay, so this is a very interesting problem. Now if there was no rotation, then this half I omega square term will not be present in our calculation. So this is coming explicitly for the rotation of the cylinder. Okay, okay. Now I will ask you to do it for the sphere also. Just substitute this k by s r square as 2 by 5 instead of 1 by 2 and follow the same procedure. You can find what will be the distance for a sphere. Okay. Okay. Now this was some application of the moment of inertia tensor and our knowledge of conservation of momentum and all other things. Okay, now we will do some. Oh, I have a problem in my mind, but that I will do later. But first, some fundamental thing will do. So okay, so you have learned that principle of moment of inertia and all that stuffs in class. So we can write our L1 as I11 omega 1 I12 omega 2 plus I13 omega 3. Now if we go to our principal axis, it can be written as I omega 1, right, where omega 1 is the angular velocity with respect to the principal axis. Similarly L2, this also can be written as I omega 2 L3. Okay, so I mean ideally it should be like this, 2 3 omega 3, but for a principal axis we can write it like this way. So similarly I omega 3. Now suppose you have given a body, and body means object, and you have been asked to calculate what are the principal axis of that body and what are the principal values of moment of inertia. Okay, so we will calculate that for today. Now from this system of equation, one thing you can write, that is, what is that, 30 mr square, just a second. Yeah, so yeah, so when you are going to your moment of principal axis, then you have to solve a particular determinant, which is called the characteristic determinant. That is, if you solve I11, first write I11, I12, I13, I21, I22, I23, I31, I32, I33. Okay, and this minus I omega 1, omega 2, omega 3 equals to 0. So if you solve this particular determinant, so I am just telling you to how to solve. So I am giving one new numerical prescription, you can say. so that you can solve the problem. So if you solve this particular determinant, you can get the value of the principal axis and also the value of the moment of inertia. Okay, so for this thing, I mean, how I do the how I write this. So for that I will ask you to go to the SAS class and you can understand how to do it. Okay, so yeah, and you can see that as it is a system of 3 equations, right? So it will give me, instead of one I, it will give me I1, I2 and I3, and those I1, I2 and I3 are the principal moment of principal moments of inertia of a particular body. Okay, now let us come to a body. So suppose yeah, I will take the help of books for this problem. Okay, so suppose this is a body, this is a laminar body, and we have taken our axis like this. I mean, this corner point we have taken it as our coordinate center. Okay, so let us call it x2, it is x1, it is x3. Okay, and the unit vectors are small x3, small x1, small x2. Okay, now let's give it a name 0a b c. So it is a rectangular or square lamina, whatever you can say. Now, so first we have to calculate this I11, I22, I33 as well as the cross terms for this particular system. Okay, so I11 and I22, if you calculate here, it will be, so for the lamina example I have done it in the previous class, you can go to that also. And also we have to consider surface density of a particular system. So let us consider the surface density as sigma, so this will be x2 square. So here I don't have I11, I22 sigma x2 square dx2 dx1. Okay, so just 0 to a because I have taken this as a, I mean it is a sphere, so let us say a square and a is the size of the arm. So if you calculate, you will get 1/3 m square, where capital M is the mass of the system. Okay, it is very trivial and I have also done that, so go to that. It is your I11 and I22. Okay, so your M is actually a square sigma. Okay. Now yeah, now from okay, so just listen it very carefully. By mistake I have some, I mean, in some time I have called, if I have called it at perpendicular axis theorem, so that is not correct, that is my mistake. It is actually parallel axis theorem. Okay, so yeah, I have written it in a correct way, but sometimes I may have pronounced it at a perpendicular axis theorem, but that is wrong. It is parallel axis theorem, because you can see your distance from the point of observation is actually parallel distance a square. So there is no perpendicular direction in this case. It is parallel axis theorem. Remember, that is my mistake. But perpendicular axis theorem is applicable only for a laminar body. Okay, so that also I have done in the previous class. So if your body is like this, where your x3 coordinate is coming out of the paper, which is perpendicular to the body, you can say, so moment of inertia along that particular axis, which is perpendicular to the laminar body, that can be written as the sum of other two direction, which is in the plane of the body. So it is called the perpendicular axis theorem, because there is some perpendicular direction in this theorem. I mean that I33 is perpendicular to the laminar body, and as it is called a perpendicular axis theorem, we should have a perpendicular, so it is applicable for a laminar body only. You cannot apply it in any other case. So if you have calculated I11, I22, so I33, it will be 2/3 m square. Okay, so our I11, I22, I33, all this done. Now we have to calculate the dot products. Now as it has no x3 coordinate, so the dot product which involves the x3 part, that means 3 1 3 2, those will be 0. Okay, and the non-zero part will be just I21 I12, all those cross terms which is in the plane of the body. Okay, so if you calculate I21 I12 also, then all this thing how to calculate it for a laminar body I have done in the previous class, so you can go to that. Okay, 0 to a x2 dx2, and it will give you minus 14 m square. Okay, just do it. So this is the value, and other which involves 3, that is 3 1 1 3 3 2 2 3, all will be 0 because there is a third coordinate which is perpendicular to the body, so that is 0 for the body. I mean the position in the x3 coordinate is 0 for the body. Okay, so now let us write it in the determinant form. So I11 was 1/3 m square, so 1/3 m square minus I. Then I22, that was also 1/3 m square minus I, and I33 I mean 1 2 3 I am using for x, y and z. Okay, so 2/3 m square minus I, and all the cross terms which are non-zero, this one only, and all other terms are 0. Okay, this, so we have to, this is equals to 0, this we have to calculate at first. Right. Now so it will give you like I 1/3 m square minus I, just the expansion of a determinant, I minus 1/4 m square minus 4 m square 2/3 m square minus I equals to 0. Okay, so you can see it is a cube equation in I, that's why we will get 3 values of I, and if you calculate it carefully, I will not do that in this because that will take more 15 to 20 minutes. So if you calculate this, just do it, and some algebraic manipulation, so it will be like this. So all this will be in YouTube, and you can check it by pausing the video also. Okay, it will be 0. So from this you can get the values of 3 values of I. So let us, I will write 1/12 m square, I2 7/12 m square, and I3 2/3 m square. Okay, now these are your principal moment of inertia. Okay, now we have calculated the principal moment of inertia, but till now we have not calculated the which are the principal axis. So there must be some axis corresponding to every principal moment of inertia, right? So that now we can calculate how. Just substitute your I1, that means just substitute those 3 values one by one in this particular particular equation. So if you substitute your I1 1/12 m square, so just write 1/12 m square in place of this I for that I1 value, then you will get okay, so yeah, and I have written here, so there is omega 1, omega 2 and omega 3 also. As this is non-zero, so it I mean this column vector is not 0. Okay, so the column vector is there. Now just write that vector omega 1, omega 2, omega 3 is equals to 0, that means 0 0 0. So it, as it is a vector equation, you should write it in this way, then and substitute your I1 at first, then I2 and then I3. Okay, so now if we substitute the I1 part, then what you will get from this equation, that is please check all this, because it is not possible to do all this calculation in the class. Okay, square omega 2 plus 0, it will yeah, so it will be the first one. I mean you will multiply this with this, and that is equals to 0. So this is the first equation. Now the second equation will be 1/3 m square minus 1 by 12 m square omega 2 plus 0 equals to 0, and the third one will be this m square omega 3 equals to 0. Okay. So this is the three equation corresponding to only I1. Okay, so I have not used the I2 and I3 in this equation. It is only this three equation is coming for only I1 if you substitute the I1 in the determinant. And if you calculate from this set of equation, you will find omega 1 is equals to omega 2 and omega 3 equals to 0. Okay, so what does that mean? That means your omega, which can be written as x1 omega 1, x2 omega 2, x3 omega 3. Okay, so this part has gone, so x1 omega 1 plus x2 omega 2 is there. So you can see this is your omega corresponding to that half m square, which is the first value. Now what this actually says, that is the important thing. So it is x1 plus x2. Okay, so this will give you your axis, I mean principal axis. Okay, so it was our, this was our system. Let us copy it. Yeah, okay, so this was our system, and you can see now your rotation axis is actually x1 plus x2. Okay, so this was our x1, this was our x1, and this is our x2, I mean unit vector. So x1 plus x2 will be this vector, right? This vector is x1 plus x2 vector. Okay, so that I1 1 by 12 m square, this value of moment of inertia is actually corresponding to this axis, which is the, you can see say the diagonal of the particular lamina. So the diagonal of the lamina is a principal axis of rotation. First axis of rotation we have got from our I1, and that is the diagonal. Now if you, in the similar way, if you substitute your I2 in that particular equation, so if you substitute your I2, for that case you will get omega 1 equals to minus omega 2 and omega 3 equals 0. So and your final omega will be x1 minus x2 omega 2 because of this minus sign. Okay, so x1 minus x2 coordinate is actually this coordinate, which is perpendicular to the OB axis, right? So this OB axis was your first principal axis. Now this O, whatever you can say D, which is just 90 degree, just making a 90 degree angle with the OB axis, that is our second principal axis, and corresponding value of I2 is this one, 7 by 12 m square. And if you calculate, if you substitute your I3 2/3 m square, so for that case you will get, so for I3 you will get omega 1 equals to omega 2 equals to 0 and omega 3 non-zero. Okay, so that means this axis is actually x3 axis, because there is no x1 and x2 components. So your three principal axis of rotation is the OB axis, OD axis, and the x3 axis itself. Okay, which corresponds to 2/3 m square, and it is obvious, it is quite easy to see this particular value, this 2/3 m square. So you can see this 2/3 m square has come in here also, which was the I33. So by solving the determinant you are getting the same value 2/3 m square. So at that instant it is telling that your I33, which is correspond to that x3 axis, is one principal axis of momentum and the principal value of inertia. Okay, so this is how you can calculate for any type of body the principal axis of principal axis of inertia, principal moments of inertia, as well as the principal axis also. Okay, so I think you have understood. And if you have any problem, just ask, because it is a very important concept and it is a very important numerical recipe to how to calculate principal axis for a particular body. Okay. So very for for recapitulate, I will very first go through the process. Just solve this particular determinant with the cross terms. It is not 0, okay. So I1 2 I1 3 and all those terms. So just solve this equation, which will give you three values of I1, I2 and I3, and these three values are exactly your values of principal moment of inertia. Okay, now just substitute that value in this equation. In this is same as this, just I has been substituted by I1, I2 and I3 with omega 1, omega 2 and omega 3 equals to 0, 0, 0, and you will get three equations corresponding to every I, and solve those three equations. That will give you the values of omega 1, omega 2 and omega 3, and write your omega as a combination of this. Then from the values of omega you can say which is your principal axis of rotation. Okay, so this is the main thing and it is quite important. Okay. And you saw that for this type of body, this is one principal axis of momentum, this is one, and x3 which is perpendicular to the body. Okay, so these are the three moment of axis of rotation with the principal moment of inertia, which has been given by what was that 1 by 12, one is 7 by 12 and another is 2 by 3 m square. Okay, so this is a problem. Okay, yes, any question?
Yeah, I want to ask one thing.
Yes.
So in the lecture, sir told us that there are three types of bodies, how he has categorized it.
Okay.
One is spherical, another is symmetric, and another is asymmetric.
Yes.
For yeah,
So
so
that depending on I mean the moment of inertia, right?
yeah,
Yes.
that's depending of differential, right?
Yes.
So I want to ask for asymmetric part.
Yes.
Is it possible to find the principal axis? Like is it possible that if we direct the moment of inertia towards one of the principal axis, then I just want to know if it's possible.
Uh,
Because for spherical, obviously it's
it's
possible,
possible.
but
Yes.
neither of them is possible. So for symmetric, you can use one.
Yes.
It's symmetric around one of the
One
axis.
axis.
But what about asymmetric?
Okay.
Because in the asymmetric, sir just said that we need to explicitly find it, which is pretty obvious because it's not symmetric to either of the axes. And then he said that we need to, according to some coordinate axis, find it and then diagonalize and then you find principal axis.
Diagonalizing mean this particular method which I shown here. That is yes.
So like it's something like back calculating and then finding the principal axis, right? Asymmetric.
Okay, so I will go through in details the asymmetric part, as it is very complex. No one goes through it, so I will let you know in the next class, because without without doing that it will not be a good idea to tell right now. So I will let you know in the next class whether how we can find and whether we can at least find or not. Okay, for the asymmetric body, yeah, I will remember this.
Another thing I want to ask you, so for the recent assignment,
Yes.
assignment 8 ka second question mein,
Mhm.
sir
Yeah, I have also gone through the lectures. He have not said precision till now, till this point, right?
Yeah, he has. So if you want, I'll read out the question. The question he is having here. So the question is: Imagine a rock that is symmetric, cylindrical in shape, a symmetric top. It is thrown deep in space away from a source of forces. It is then observed to move towards an inertial frame of reference. It moves with continuous mass and rest. A
Okay.
student claims that as the rock is symmetric in shape and there are no forces on it, the rock can only spin and there cannot be any precession. Is the student's claim correct? So, what is this precession? Can you explain?
So precession means actually, I mean there is two thing. One is precession and one is nutation. So precession means as far as I remember, like you have a top like this. Okay. So this top can yeah, this and it is OA axis. So it can rotate around this OA axis, which is the axis of this particular system. So it will rotate like this. Okay, I mean this pen, it is rotating like this. So while rotating like this, it can rotate like this also around. I mean, suppose this is your another axis, and it is rotating like this. Okay, so yes, this is actually the precession thing.
Okay.
I
So
mean, it can rotate about this axis also and about another axis also at the same time.
wait, what? About yeah, it rotates along axis of symmetry,
I-
like what you're saying.
That is OA, and at the same time, it can rotate around this OA axis also. I mean, this will make a path like this.
True, true. That would make a path. So basically, you're saying it can rotate along another axis, which is kind of parallel to OA axis.
No, not parallel. It must make some angle because of the precession. Because if it is the body in a more simplest version, so there must be some angle to get this type of motion, right? Yeah. So this type, I mean, this is
And angle where that motion is called precession. Is that what you're saying?
yes. As far as I remember, this is actually called a precession. So it is not rotating around its symmetrical axis. It is rotating around some other axis. I mean a rod which is slanting at some position, and it is rotating like this.
Yes. So this is something which
So
is on the axis, right?
yeah, just a second, just a second. So, yeah, I think if this is the top, it can rotate like this axis, this pen. Okay, like this.
Okay, got you.
Okay. So can you hear now?
Yes.
Yeah, so if this pen is the body and this is the axis, so it can rotate around this axis.
Okay, so it's basically a space coordinate. Is
Yes,
that what you're saying?
yes, this rotation. Okay. And that asymmetric part I will tell you in the next class after going through it. Yeah.
So with principal axis, any of the axis which is what it means by principal axis?
I mean,
Like what it
about that principal axis, all the cross terms are zero. You can write your I as, I mean, as here I have.
so the diagonal elements will be there.
Yeah, exactly, yes. That's why we in in terms of physics you can say diagonalization. So you can see that only the I omega 1 is there, no I 1 3 or I 1 2, only this part is there.
So this is a very similar concept in many of the other concepts we
This
have.
concept you can find it in small oscillation also. By the same formalism we have calculated the normal modes, the normal frequencies.
Yes.
So the normal frequencies are exactly like this moment of inertia in this case, and the normal modes are exactly like the principal axis for this case.
True, true.
Those are exactly similar type of concept.
Got it.
Okay, okay, no problem. Okay, so then I had a problem, but I can do it in the next class. I mean, I can ask you to do it. Just try to calculate the moment of inertia of a cone about its symmetrical axis. So, I have calculated the moment of inertia of a triangular lamina. You can get some idea from that part also. Okay. So just try to do that. And another very quick thing. I mean, I thought it is important. So could you post solution of assignment? So actually I have not explicitly done the solutions. I have gone through what type of problems is there. So if you have to ask something, you can ask here, but I don't have done that explicitly to post. Okay.
Some of the problems are don't know how to do to solve the problem.
uh, like can you say, I mean, then I will go through those problem in the next class, or can you mail me those problems?
Sir, assignment 7, 6 are
Assignment 7. Hello.
I think yes, sir. Something difficult to solve 6 and 7.
Okay, so I cannot hear you clearly, so can you just email me the assignment number and the problems? Can you do that? I just can hear the 7.
Yes, yes,
So you know my email ID, right? Okay, it is this email
yes,
ID.
I know your mail ID.
Okay,
I
okay.
I know I know your mail
Okay,
ID.
still okay.
Then I have a doubt on assignment 6. What's the question?
Okay, then we can go through those problems in the next class. I mean, if there is problem, we should do. Okay, no problem. And assignment 6 3 and assignment 6 3. This I can hear, but I cannot hear from Krutika actually what she is telling. Okay, just mail me the number. I will go through those problems in this week. Alright. Okay, then we can end it today, and we will meet the next.
Yes, sir. Thank you,
Yeah,
sir.
thank you.